All right, welcome to this explainer, everyone. Today, we are going to build the entire architecture of calculus, literally from the ground floor up. We'll be transforming some pretty dense mathematical theory into logical, manageable building blocks. And the goal here? To help you completely conquer the calculus sections of the JEE main. Let's get right into it.
So here's our roadmap for today. We are going to cover limits, continuity, differentiation, the engine of derivatives, and finally how to apply all of this to master the JEE main. Starting off with Part 1, Limits, our crucial foundation.
We absolutely have to start right here, pouring the concrete for our foundation. Because, look, before we can ever hope to measure the rate of change, we really have to deeply understand the concept of approaching a destination. You see, a limit isn't about what happens exactly at a specific point. Not at all. It's actually about what happens as we get infinitely close to it. It's all about the journey. Mathematically, as x approaches a, we just want to figure out where the function assumes it's going. Basically, what's the target destination?
But here's the catch. For a limit to actually exist, the path approaching from the left, which we call the left-hand limit, and the path approaching from the right-hand limit, they must physically meet up at the exact same location. If you're walking along those two paths and they point to completely different destinations, well, the limit breaks down. It simply does not exist. Okay, I need you to burn this table of standard limits into your memory. Just look closely at these relationships, like the limit of sine x over x as it approaches 0 equaling 1. You know, these aren't just arbitrary equations. These are the foundational anchors you are going to use to quickly bypass those messy, time-consuming calculations on the exam. Truly, these are your essential shortcuts. Of course, sometimes you're going to run into an indeterminate form, right? Like 0 divided by 0. When you hit that kind of roadblock, whatever you do, don't panic. Just follow these step-by-step actions to clear it out. For type 1 algebraic limits, you can often just clear the path by factoring out the problem term. And for type 2, which usually involves roots, you bypass the block by rationalizing. You just multiply the numerator and the denominator by the conjugate, and you're good to go. Moving on to Part 2, Continuity, where we connect the graph. Let's stack the next set of blocks onto our foundation and look at continuity. This is really all about ensuring our mathematical path is completely unbroken. If a function isn't perfectly connected, it's suffering from a broken path. It might just be removable discontinuity, which is kind of like a small pothole in the graph. Or it could be a sudden jump across a gap because the left and right limits completely missed each other. Sometimes the path completely tears apart, tending straight to infinity, or it devolves into this wild, infinite oscillation. But this right here brilliantly illustrates how robust continuous functions truly are. If you take two continuous paths, you can add them, you can find their difference, multiply them together, and even divide them. And guess what? As long as the denominator isn't 0, the resulting path remains completely solid and unbroken. They stack together perfectly.
Next up, Part 3, Differentiability, Finding the Slope.
So now we reach a critical transition. We are checking not just if the path is connected, but if the path is smooth enough to find a definitive slope. Differentiation is the mathematical confirmation that a curve is perfectly smooth at a given point. By taking this specific limit of the difference quotient as h approaches 0, we're basically proving that there are 0 jagged edges, and that allows us to balance a tangent line exactly on that single perfectly smooth point.
Now, the crucial thing to remember here is this classic one-way street. Differentiation implies continuity, but continuity absolutely does not imply differentiation. Think of it like this. A perfectly smooth path is always, without a doubt, connected. But a connected path isn't always smooth. It could easily have a sudden, sharp spike.
And oh man, this right here is a massive trap frequently set in the JEE main. The absolute value, or the modulus graph, is completely connected from end to end, no breaks at all. But that sharp, violent V-shaped corner at exactly 0, that mathematically breaks differentiation. You simply cannot balance a single flat tangent line on the tip of a sharp point. Just won't work.
All right, let's dive into Part 4, the engine of derivatives. Let's move up to the next level of our architecture and power up the core engine of calculus, the derivatives. The derivative is the active machinery that allows us to essentially freeze time. It lets us calculate exactly how fast something is changing at a single, infinitely small instant. It literally takes the abstract concept of limits that we built earlier and transforms it into a concrete, measurable slope.
Take another mental screenshot of this table right now.
These basic and trigonometric derivative formulas, they are the individual gears that make your calculus engine actually turn. Knowing that the derivative of sine is cosine, or knowing exactly how the power rule works, is absolutely essential. Honestly, if you don't know the gears, you just cannot operate the machine.
And when those basic gears get combined into more complex machinery, you have to carefully deploy the algebra of derivatives. The product rule and the quotient rule are your strict blueprints. You use them to calculate the rate of change for multiplied or divided functions without breaking the entire mathematical system.
Now, I actually want to slow down deliberately for a second here, because mastering the chain rule is absolutely non-negotiable for your success. You master it by peeling it back step by step. First, always identify the outside function and the inside function. Second, take the derivative of the outside while leaving the inside totally untouched. Third, multiply that whole result by the derivative of the inside. Outside first, then the inside, every single time.
Once you actually have the derivative, what does it do? Well, it acts exactly like a navigational compass. It instantly tells you if a function's path is climbing uphill, meaning the derivative is positive, or if it's sliding downhill, where it's negative. It gives you the exact slope of the tangent line. And by simply taking the negative reciprocal, it hands you the slope of the normal line on a silver platter as well.
Finally, Part 5, Mastering the JEE Main.
So let's put a roof on this architecture and directly apply everything we've built today to our ultimate goal: conquering the exam itself. The exam writers are consistently going to test your structural integrity. They're going to throw piecewise functions, those tricky modulus traps we talked about, and complex tangent questions your way just to see if your foundation holds up. They want to know for sure if you can evaluate limits via standard forms and confidently test for continuity across really tricky intervals.
So, use this rapid-fire checklist as your ultimate diagnostic tool before exam day. You need to make sure every single mathematical block is firmly in place. Ask yourself, are your standard limits memorized? Are your discontinuity types known? Are your product, quotient, and chain rules locked in completely?
Because now that you know exactly how the fundamental engine of calculus works and how limits, continuity, and differentiability all fit together so seamlessly, the only real question left is, how far will you let it drive your success?